Now, this next part will look similar to 7.1 as well. So this is different styles of questions we may be asked and different styles of questions we can solve. Let's say we want to calculate the point estimate of the population mean. Remember, the point estimate of the population mean is x bar. X bar is our sample mean. So if we want to calculate the sample mean, then we can calculate the point estimate of the population mean by finding x bar is equal to the upper confidence limit plus the lower confidence limit divided by 2. Again, we're sort of taking the mean of these two values. Additionally, we could solve for the margin of error value if we're not given that in the problem. So to do that, we find capital E, or the margin of error, is equal to the upper confidence limit minus the lower confidence limit, all divided by 2. Now we're transitioning again to a different style of question. So we're going to find the sample size required to estimate a population mean. The style of formulas here should feel very comparable to 7.1. So now in 7.2, we'll talk about finding the sample size now required to estimate a population mean. This is different than 7.1 when we're working with population proportions. The objective is what you think it'd be, so we will determine the sample size n required to estimate the value of the population mean, or mu. Let's go through the notation now for this kind of question. So mu is our population mean, sigma is our population standard deviation, x bar is still our sample mean, E is our desired margin of error. Now be careful here because this comes back. Now we're again working with z subscript alpha over 2, which is our z-score separating an area of alpha over 2 in the right tail of the standard normal distribution. Now remember, this is different than t subscript alpha over 2 because t subscript alpha over 2 was for t distributions and z subscript alpha over 2 is for standard normal distributions. Let's go through the requirements again. So the sample must be a simple random sample. That's a requirement you're used to seeing. Now, to find the sample size n, we'll use this formula. So n is equal to z subscript alpha over 2 multiplied by sigma, all divided by e, the margin of error, and all of this is squared. What's the meaning of each notation now? So you should hopefully be familiar with this. N is our sample size required. Z subscript alpha over 2 is the corresponding z-score for a standard normal distribution. So it's that z-score that separates on the right-hand side that area of alpha over 2 from the rest of the standard normal distribution. This sigma value is our population standard deviation. E is our margin of error. Then we put all this in brackets or parentheses and we square that. Let's talk about the round off rule here. So if the computed sample size n is not a whole number, then we round the value of n up to the next largest whole number. This is the same round off rule you saw in 7.1 when we were also estimating the minimum sample size for a population proportion. Remember, in 7.2, we're working with population means rather than population proportions. And importantly here, if you're asked a question about estimating the sample size, then start to think about z subscript alpha over 2. Now you'll notice that sigma, or the standard deviation of the population, is within this formula. Well, sometimes we don't know that value of sigma. We don't know the population standard deviation. So when we don't know sigma, this is what we can do. Number one, we can use this idea of the range rule of thumb. You've seen that before. We can use that to estimate the standard deviation by taking sigma, the population standard deviation, is approximately equivalent to the range of the data divided by 4. Now, note here that the range is determined from sample data rather than population data. Number two, we can start the sample collection process without knowing sigma, and then using the first several values, calculate the sample standard deviation S and use it in place of sigma. So again here, what I mean is that we start to actually collect the data, then with each of those sample data points, we can get an estimate of S. The sample standard deviation is S. we can use the sample standard deviation then in place of sigma. We will get a better estimate of sigma, the population standard deviation, if we're using more and more and more samples to estimate the sample standard deviation, or S. So in a perfect scenario, we'd start to collect data, then with each of those sample data points, we find S, then we collect many, 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 many more to then use the sample standard deviation, or S, in place of sigma, which is our population standard deviation that we're interested in. Again, why we need sigma, our population standard deviation, is because it's in our formula to find n, the sample size. Or number 3 here, we can estimate the value of sigma, the population standard deviation, by using the results of some other earlier study. Either way, though, we need some estimated value of sigma, our population standard deviation. Just to remind you again of this formula, so we need to plug in some value here in order to estimate our sample size required to estimate a population mean. So we need sigma in order to get n here when n is unknown. Let's do an example now using IQ scores of students. Assume that we want to estimate the mean IQ score of the population of students. Just completely arbitrarily, let's say the range is from 80 to 140 as far as IQ scores. Let's answer this now. So how many statistics students must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? Let's start looking at what we know for this solution. So for a 95% confidence interval, we know in a non-percentage that's equal to 0.95. We're doing this because we need that z subscript alpha over 2 in order to calculate n. So with this confidence interval of 0.95, we find the complement in order to find alpha. So 1 minus 0.95, that's 0.05. Now, what's nice about this 95% confidence interval is that it's one of the most common ones we use. So rather than going through and calculating z subscript alpha over 2, we can go back to 7.1 and find that table of the most common confidence intervals. In that table, we'll have our confidence intervals, we'll have the alpha value, and we have the corresponding z subscript alpha over 2 already provided for us. Again, you should be able to calculate this value of 1.96, but if it's already given to you and you are comfortable doing so, then you could just take 1.96 from the table and then move forward in this problem. You'll get practice calculating z subscript alpha over 2 in your 7.1 homework. So let's keep talking about what we know. We also see this statement here. So the sample mean is within 3 IQ points of the population mean. Well, within 3 IQ points of the population mean, or mu, how we interpret that is the margin of error. So again, within 3 IQ points, that's our margin of error, so E is equal to 3 here. Now, from the problem, we were not given the population standard deviation, so we need to figure out what estimate we can use for that. We were given the range of IQ scores, that arbitrary range, so we can estimate sigma by doing the following. We can take sigma is approximately equal to the range divided by 4. In our problem, we were told the range is between 140 and 80, so we take 140 minus 80 is 60, 60 divided by 4, that's 15. So now in our equation to figure out n, we can substitute in sigma, our population standard deviation, as 15. Here's that equation again. So n is equal to this critical value times sigma over e, all of that squared. Let's start plugging in what we just figured out. So that's really equal to 1.96 multiplied by 15, our estimate for sigma, divided by e, the margin of error. We take all of that and we square it. When we do that, we should get 96.04. Then we have to consider our rounding rule here. Remember, for estimating n, or the sample size, we always round up to the nearest whole number. So 96.04, we make that our answer of 97. So we can do the math, we can do the statistics, we can do the Excel formulas. Let's also talk about the interpretation here. So because we figured out this answer of 97, what we can say is that among the thousands of statistics students, we need to obtain a simple random sample of at least 97 of their IQ scores. Remember what we just calculated now, so that was n, that's the minimum sample size here. So we need to obtain a simple random sample of at least 97 people, at least 97 students here. Connecting this back to our 95% confidence, we can also say that with a simple random sample of only 97 statistics students, we will be 95% confident that the sample mean, or X bar, is within 3 IQ points, or the margin of error, of the true population mean, mu. This interpretation here is really important, so make sure we can do the calculations and also understand the meaning of our calculations. Remember also that when solving for n, the sample size, we actually went back to using that z subscript alpha over 2, so keep that in mind. Also, this last example is when we didn't know sigma right away. Let's go through now estimating a population mean when sigma is known. So if somehow we do know the value of sigma, the population standard deviation, but we don't know the population mean, which is a truly rare scenario in statistics, then let's continue. Let's say we do know sigma, the confidence interval is constructed using the standard normal distribution instead of the student t-distribution. Again, this is for the very rare scenario that we do know sigma, but we don't know mu. So we know the population standard deviation, but we don't know the population mean. If this is true, that we know sigma and we're trying to estimate mu for the population, then again, we use a standard normal distribution instead of a student t-distribution. We follow the same procedure, except we use this formula to calculate E, the margin of error. Notice here the slight difference in how we calculate E. So again, we take Z subscript alpha over 2 because we're treating this as a standard normal distribution. We're using this definition of the critical value rather than that of a t-distribution. Then again, because we know sigma, we know the population standard deviation, so we multiply the critical value as far as a z-score times sigma, all divided by the square root of n. If we don't know sigma, then go back and look at how we calculated the margin of error. It's just very slight differences in the values we use here and the value we use here. Again, this slide is when we're estimating a population mean when we know sigma. Let's do an example of this. Let's say we do know sigma, but we don't know mu, and we want to estimate that. We're going to use this formula for the margin of error. We're going to follow all the same steps we did in the first part of this lecture. So let's say we're using this example here. Use the 15 birth weights of girls given below here for when n, the sample size, is equal to 15, and x bar, the sample mean, is equal to 30.9 hectograms. So Hg here is in units of hectograms. It's not a capital H where we're looking at mercury, for example, where Hg is a symbol for mercury on the periodic table. So here we're going to construct a 95% confidence interval limit of the mean birth weight of all girls by assuming that sigma, so we know the sigma, is known to be 2.9 hectograms. Here's all of our different weights. Here's all of our different sample data. We have 15 data points total. Remember, we're following the same procedure as earlier, so the first step here is to check the requirements. Number 1, the sample is a simple random sample. Yes, that's true. We weren't taking biased samples of data. For example, if we knew all of the mothers were a certain age, then that would be a biased sample. This is just a simple random sample of babies' birth weights. Number 2, because the sample size is n equal to 15, then this requirement that the population is normally distributed or the sample size is greater than 30 can only be satisfied only if the sample data appear to be from a normally distributed population. Based on just looking at the data, we can't say with certainty, is that a normal distribution? What we can say is that n equal to 15, well, that's definitely less than 30. So in order to continue on with this question, we need to ensure that this is from a normally distributed population. Because on the other hand, we can't make n equal 15 suddenly become n is greater than 30. So this may sound familiar now. We want to assess for normality. There was a section where we went through this, so let's go into it. We saw this previously in 6.5 when we were assessing for normality. In 6.5 specifically, we made these normal quantile plots, and we analyzed the normal quantile plots for normality. If we were not given a normal quantile plot, we'd have to construct one, and we go through that in 6.5. So for a refresher on making normal quantile plots, we can go back to 6.5. Let's say we were given this, or we constructed this. So here's our x values, and here's our z-scores. For each of our x values, we found the corresponding z-score, and then we plot this data as z-score versus the x value. If you remember how we look at this and say with certainty that, oh yes, that is a normal distribution, then the population distribution is normal if the pattern of the points is reasonably close to a straight line. Beyond this check, we also have to say that the points do not show some systematic pattern that is not a straight line pattern. If you go back to 6.5, one example of a systematic pattern that is not a straight line pattern is when our data were sort of in a sigmoidal curve. So from this normal quantile plot and from these checks, we can say that the sample data appeared to be from a normally distributed population. Now that we've gone through the requirement checks, now we can solve this. So one way we're going to solve this is using Excel. This is another new formula now, so we're going to use confidence.norm. We're going to use this function in order to make a step towards constructing our confidence interval. Remember, we're constructing a confidence interval in order to estimate the population mean, or mu. It's important to remember why we're going through all these steps rather than getting lost in the details here. So the big picture is we're trying to estimate mu, our population mean, when we know our population standard deviation, or sigma. Let me show you how to set this up in Excel. So the first row I did was labeling n, my number of samples. We had 15 different weights we were working with. We were also given x bar, the sample mean, that's 30.9. In the question, we were also given our population standard deviation, or sigma. We can assume that to be 2.9. We were told to work within this confidence interval of 95%, taking that out of a percentage, that's 0.95. A step I can do next now is to find alpha. Remember, I'm taking alpha plus my confidence interval to be complements of one another, so I can take 1 minus my confidence interval to find alpha. When I take 1 minus 0.95, I get an alpha value of 0.05. Then using this new function now, so we know sigma, we're trying to estimate mu, then we're next going to find our E value. Let's go through this now. So I type in equal sign confidence.norm, open parentheses. It's telling me to put in my alpha value again. So my alpha value is 0.05. I'm not putting in alpha over 2. I'm putting in alpha value of 0.05. The only other two values I need for this function is my standard deviation, which I know now. So that's why I'm using this function. So I do my alpha value, my standard deviation, and the size. So in this function, I have 0.05, comma, my standard deviation of my population, 2.9, comma, the size, so I had 15 babies' weights. Again, practice doing these functions along with me. Next, using Excel, then I hit enter. I got this value for my confidence.norm. That's really E, my margin of error. Then similarly, to construct my interval, I want to take x bar plus E and x bar minus E. My X bar value is my sample mean that was told to us in the question, so 30.9. I want to take 30.9 plus this value I just got from the confidence.norm function, or my E value. Finding X bar plus E, the margin of error, I'm going to do here. Then I also want to find X bar minus E. When I click enter and get these values, then I get longer versions here. Then I can use Excel to help me round off. Remembering that there are two different ways to round off, well, we used our original set of data here. So we can go one more decimal point past our original set of data. In Excel, that button looks like this. So I want to decrease my number of decimal places. I get X bar plus E is 32.4. X bar minus E is 29.4. Now that I have the upper end and the lower end of my interval, then I can plug those values in here to get 29.4 is less than mu, our population mean, which is less than 32.4. Again, I recommend practicing doing this along with me in Excel. Now, we can also do this without Excel, and we can follow pretty similar steps now for a manual version of solving this problem. So to solve this manually, we'll go through the same sort of line of thinking. We have a 95% confidence level. That's really equal to 0.95 when we take that out of a percentage. To find our alpha value, we take 1 minus 0.95, that's 0.05. Then we could go back to 7.1. We know a 95% confidence level is one of the more common confidence levels, so we can find a z subscript alpha over 2 is equal to 1.96. We could also definitely calculate this, and we should know how to do so. So we have a z subscript alpha over 2 of 1.96. That's our critical value now. We also know our population standard deviation is 2.9 hectograms, and the sample size is 15. So instead of using Excel to solve for E, we can do this manually by using this formula. We want to find E is equal to this critical value as far as a z-score multiplied by sigma all over the square root of n. If we plug in the values that we know now, we know our critical value is 1.96. We know our standard deviation for the population is 2.9. That was given to us in the problem. Then we take the square root of n, so that's 15 different baby weights. Again, you can either use that new function in Excel to find E or do this manually. So we find an E value of 1.46760. Once we know our E value and we know our X bar value, then we need to construct that interval. To do this, we take X bar minus E and X bar plus E again. Plugging in the values that we know, here's our X bar value, 30.9. Here it is again. Here's our value minus E. Here's our X bar value plus E. Just to reiterate again, this is when we know our sigma, our population standard deviation, and we're trying to estimate mu, our population mean. When we plug in and solve for these values here in our interval, then we get this value here, 29.4 on this side, 32.4 on this side. We needed to consider rounding here. We went to 1 decimal place and we included units here because technically this population mean is greater than 29.4 hectograms, but then it's less than 32.4 hectograms. Okay, so try doing this with Excel, try doing this manually, see which way you prefer, and get really comfortable using both methods. When doing these sorts of problems, it's still important to keep in mind that knowing the population standard deviation is rare. Truly, the more realistic situation is when we don't know sigma. So that's what we covered in the first part of 7.2. So either we knew sigma, and we just did the example when we knew sigma. If we don't know sigma, we still need some way of estimating it. We talked about how to estimate it. We can use the range rule of thumb. We can use previous data. We can start collecting sample data and then estimate a sample standard deviation as our population standard deviation. The last slides of 7.2 are this table. So when deciding on choosing an appropriate distribution, then we can consider the conditions and then the following method. So given the conditions that sigma, our population standard deviation, is not known, and a normally distributed population, or sigma is not known and n is greater than 30, then we use a student t-distribution. Now, in this row, when we have the conditions that sigma is known and we have a normally distributed population, or sigma is known again and n is greater than 30, again, the key differences here is when sigma is not known and when sigma is known. Keep in mind again that sigma is rarely known, but in these cases, we use a normal z distribution. Then this last row here, a population is not normally distributed and n is less than or equal to 30. We would cover that in 7.4, but 7.4 is not in the scope of our class this semester. We're at the end of chapter 7 now, so in chapter 7, we're covering 7.1 and 7.2. Next time, we'll move on to chapter 8, so I'll see you then. I hope you're all doing well. Talk to you later.